Every year, about 3.8 million people die from this invisible killer. And it's not a virus or a waterborne illness or anything. It literally claims more lives annually than HIV, malaria, and tuberculosis combined.
Yeah, it's a completely devastating reality.
And the most heartbreaking part is that it happens while people are doing something that, most of us associate with warmth and family. They're just cooking dinner.
Exactly. When you look at global health, indoor air pollution from open cooking fires is like the absolute definition of a hidden crisis.
Right.
We're talking about mothers and children breathing in the equivalent of hundreds of cigarettes a day,
Right.
simply because they need to boil water or cook rice.
It's awful. Well, welcome to the deep dive. We're jumping straight into a mission today that I am incredibly passionate about. We are exploring a fascinating project-based learning module. It's called the Fire Builder's Guide to Earthenware and Ceramics. And the material we are pulling from today is dense, it's varied, and it is honestly entirely mind-blowing. We are going to be looking at the fundamental physics of combustion, the architectural secrets of ancient Roman concrete.
Which is such a cool story.
Oh, it's so good. We're also looking at reports from the International Justice Mission on modern brick kilns and even how you can use a modified kitchen microwave to reach temperatures that rival industrial foundries.
It's a vast array of scientific disciplines. But what makes this deep dive so compelling is how all of this information converges on a single really urgent goal,
Right?
which is using engineering to solve massive human crises.
And we really have to talk about who this module was built for because that context changes everything. This curriculum is not designed for a traditional, pristine university laboratory.
Not at all.
It is uniquely designed for incarcerated adult learners studying through the Cade-Moore Polytechnic Institute, or CMTech. So these are individuals who are taking their time, their focus, and applying it to literal MIT and Stanford-level engineering concepts.
Yeah, we are talking thermodynamics, materials science, structural analysis.
And we are going to be treating these adult learners as absolute peers today as we walk through the exact same science they are mastering.
And the structure of the CM Tech module is brilliant, really, because it doesn't just hand the learners a dry textbook.
Right. Nobody wants that.
Right. It frames all of this hard science within a highly engaging, high-stakes narrative. So the learners step into the shoes of Maya Torres. She's a fictional engineering student who's been tasked with a massive challenge.
Designing clean, sustainable cooking solutions for the Rohingya refugee camps in Bangladesh.
Exactly.
And using Maya as our guide is exactly how we're going to navigate this today. We're going to follow her design process step by step. Because Maya isn't just trying to pass a test, right? She is trying to solve that 3.8 million mortality figure.
Yes, she's tackling the real-world problem.
So let's put ourselves in Maya's shoes. She arrives at the Rohingya refugee camps in the Cox's Bazar area. What is the actual reality on the ground that she's facing?
Well, the environmental and human toll she encounters is staggering. To understand the scale, you really have to look at the data before liquid petroleum gas, or LPG, was distributed to the camps.
Okay.
At that time, the camps were consuming roughly 700 metric tons of firewood every single day.
Wait, 700 metric tons daily?
Daily.
I can't even visualize that amount of wood. That's insane.
It is a catastrophic level of consumption, and the immediate result of that need for fuel was the destruction of 3,300 hectares of surrounding forest land.
Wow.
Hillsides were completely stripped bare, which of course then led to massive risks of landslides during the monsoon season.
Right, because there are no roots holding the soil together.
Exactly. And all of that wood, those 700 tons, was being dragged back to these cramped, poorly ventilated shelters and burned in traditional three-stone fires.
So just literally 3 rocks on the dirt floor, pushing a pot up with a fire underneath.
Yeah, the most basic setup possible.
Which brings us right back to the smoke and the deaths. So Maya's looking at this and realizing she has to completely rethink how these fires are built, which forces her and us to ask the most fundamental baseline question: what actually is fire?
Right.
Because if 3.8 million people are dying, clearly we've been looking at it wrong.
That is the perfect starting point.
Yeah.
So to understand why those three-stone open fires are so deadly, Maya has to deconstruct the fire triangle.
Okay, the fire triangle.
From a very young age, we are taught that fire is a thing, like a noun. But it isn't. Fire is a chemical process called combustion. And for that process to exist, It requires three specific ingredients to be present simultaneously: fuel, oxygen, and heat.
Okay, let's unpack this right out of the gate. When
Yeah.
we say fuel, specifically in the context of the wood Maya is looking at in the camps, what are we really talking about on a molecular level?
On a molecular level, wood is essentially a battery of stored chemical energy.
A battery.
Yeah, you are looking at complex chains of carbon and hydrogen atoms bonded together. That is the physical legacy of the tree, spending decades converting solar energy and carbon dioxide into a solid structure.
Oh, wow.
The fuel is those carbon-hydrogen bonds. Then you introduce the second element, which is oxygen from the atmosphere. Oxygen makes up about 21% of the air we breathe, and in combustion, it acts as the chemical reactor.
But wait, I can stare at a log in my backyard all day, surrounded by oxygen, and it doesn't just burst into flames.
Exactly, because you are missing the third element, which is heat. Heat provides the activation energy. You need a massive influx of thermal energy to forcefully break those carbon and hydrogen bonds apart so they can violently react with the oxygen.
Right.
Once you supply that initial spark and that reaction begins, the combustion process becomes exothermic. It sustains itself by producing its own heat, breaking more bonds, pulling in more oxygen, and chaining the reaction.
Okay, so if the underlying physics of the triangle are that straightforward, why do the three stone fires in the camp produce so much lethal smoke? Especially considering the wood they're foraging is often damp or completely wet.
Right, wet wood is a huge problem.
I mean, anyone who has ever gone camping or tried to start a fire after a rainstorm knows that wet wood is a total nightmare. Is the smoke we are seeing just the water boiling off?
It's much more complex and significantly more dangerous than just water vapor. When Maya observes wood burning, she isn't seeing a single action. She is watching four distinct stages of combustion happen sequentially.
4 stages, okay.
And the critical issue with wet wood is that it creates a massive, debilitating drain on the fire's thermal energy.
Walk us through that. How does the water kill the fire's efficiency?
It comes down to the conservation of energy. When wood is wet, the fire cannot focus on breaking those carbon-hydrogen bonds. Instead, the fire is forced to spend a huge percentage of its heat energy just phase-changing the liquid water trapped inside the wood into steam.
Oh, I see.
It has to physically boil the log from the inside out. And if the heat energy is being consumed to boil water, it's not being used to raise the temperature of the actual combustion zone.
It's like trying to run a marathon while wearing a freezing wet blanket.
Right.
Your muscles have the energy, but your body is spending all of its heat just fighting the cold blanket, so you can't ever reach your top speed.
That is an excellent analogy. The wet wood keeps the overall temperature of the fire drastically lower than it should be. And because the fire is cold, relatively speaking, it struggles to properly execute the next stage, which is gasification.
Gasification. Okay, this was a concept in the module that completely flipped my understanding of fire. Wood doesn't actually burn, does it?
No, solid wood does not burn.
That is so wild to think about.
It really is. As the thermal energy bakes the wood, it causes the solid material to decompose and release highly volatile compounds. It releases wood gases. It is these invisible gases mixing with oxygen that actually ignite and create the visible flame. But here is the catch for Maya in the refugee camp. In a cold, wet fire, those gases are released from the wood, but the ambient temperature isn't high enough to ignite them, so they just billow out into the air.
And this brings us to the crucial difference between primary and secondary combustion. This was the massive aha moment for me when I was reviewing Maya's curriculum.
It is the hinge upon which the entire engineering solution turns. In primary combustion, the wood is burning, but because the temperature is low, it is burning incredibly inefficiently.
Right.
In a perfect world, complete combustion, where every molecule reacts perfectly, produces only two harmless byproducts: carbon dioxide and water vapor. That's it.
But the real world, especially a damp three-stone fire, is not a perfect world.
Far from it. When the fire isn't hot enough, you get incomplete combustion. The chemical reaction is starving and staggered. And incomplete combustion produces a deadly, toxic cocktail of byproducts. We're talking carbon monoxide, formaldehyde, benzene, and massive amounts of particulate matter.
And here's where it gets really interesting for you, the listener. That particulate matter, that thick, choking smoke filling the shelters. Smoke is actually just unburned fuel.
Exactly.
It is not the inevitable exhaust or ash of a fire. It is wasted potential. It is a cloud of volatile gases and carbon particles that never got hot enough to burst into flame.
Precisely. Smoke is fuel that escaped. Which means if Maya can figure out how to achieve secondary combustion, she doesn't just vent the smoke outside. She literally uses the smoke as additional fuel to generate more heat for cooking.
But to ignite smoke, you need serious heat.
Extreme heat. According to the data provided by the Provetro Research Center, which Maya is using for her specs, you need internal temperatures above 850 degrees Celsius just to reach near complete combustion.
Huh.
And if you want to ensure virtually all of the smoke and volatile gases combust, you need to push that environment well past 1,000 degrees Celsius.
Which obviously you are never going to get in a damp, smoky, three-stone fire sitting on the dirt floor of a refugee camp. The heat just dissipates instantly into the surrounding air.
Right. It's impossible.
So Maya's engineering challenge is clear. How do we force a simple wood fire to hit 1,000 degrees Celsius? And this is where the learners at CM Tech follow Maya into the engineering elegance of the rocket stove.
The rocket stove is an absolute masterclass in humanitarian engineering. It takes the problem of heat dissipation and completely eliminates it using foundational thermodynamic principles.
That's so smart.
Doesn't ask the user to find better wood. It forces secondary combustion to happen by the pure geometry of its design.
Let's visualize this for the listener. If you were to cut a rocket stove in half, it essentially looks like a letter J or an L. Walk us through the anatomy of Maya's design. What are the core components?
There are three main components to the J-tube design. First, you have the feed tube. This is a horizontal or sometimes slightly downward angled chamber where the user inserts the fuel.
Okay.
But unlike a traditional campfire where you just pile massive logs into a pyramid, the feed tube is small. You feed sticks, twigs, or small branches in from the side. Gravity slowly pulls the wood further into the stove as the tips burn away.
And the module specifically notes that the fuel sits on a shelf or a small grate inside that tube, right? It doesn't just sit on the floor.
That is a critical detail. By elevating the fuel on a shelf, the design allows fresh, cold air to flow completely underneath the burning wood.
Because you need that oxygen constantly sweeping in to act as the reactor in our fire triangle.
Exactly. That feed tube leads directly into the second component, which is the burn tunnel. This is a short, horizontal, heavily insulated chamber. This is where the primary combustion takes place.
Okay, so the tips of the sticks are burning here.
Right. The temperature is beginning to climb rapidly, and the wood is gasifying. All of those volatile, smoky gases are being released in this tunnel.
And then those gases hit the third part of the J, which is the absolute engine of the entire system, the heat riser. This is an internal vertical chimney located directly above the burn tunnel.
The heat riser is where Maya achieves her goal. Because this vertical chimney is heavily insulated, the heat generated in the burn tunnel has nowhere to go but up.
It's trapped.
It rushes into the riser, and the temperature inside that vertical column skyrockets past the 1,000 degrees Celsius threshold.
So you have a superheated vertical tunnel. And what happens when the thick, smoky gases from the burn tunnel are pushed into that 1,000-degree environment?
They spontaneously ignite. The smoke hits that extreme thermal wall and undergoes violent secondary combustion. The smoke itself bursts into bright, clean flames.
It's just such a profoundly satisfying concept. You cure the poison by burning it. But you've mentioned insulation twice now, and Maya's notes make it very clear that insulation is the unsung hero of this entire thermodynamic system.
Without proper insulation, the rocket stove completely fails. It is the most important element. If the walls of your burn tunnel and your heat riser are dense and conductive, like, say, solid steel or heavy stone, they will constantly absorb the heat from the fire and radiate it away to the outside air.
Ah, so you lose all your heat.
Exactly. The internal temperature will constantly bleed out, and you will never, ever reach the 1,000 degrees required to ignite the smoke. You have to trap the heat inside the chamber.
But Maya is in a refugee camp. She can't exactly hop online and order aerospace-grade air gel or highly advanced laboratory ceramics to insulate her stove. She needs local, cheap materials.
And she has them. The sources detail incredible ingenuity, using materials like vermiculite, perlite, pumice, or, most commonly in agricultural regions, dried rice husks.
Rice husks, like the leftover shells from milling rice. How does that insulate a 1,000-degree fire?
It's brilliant chemistry and physics combined. First, rice husks are naturally incredibly high in silica, which makes them surprisingly resistant to catching fire themselves.
Okay, good to know.
But more importantly, it is about their physical structure. A pile of rice husks is mostly empty space. It tracks millions of tiny microscopic pockets of stagnant air.
And air is the secret weapon here.
Air is one of the greatest insulators on the planet, provided it isn't moving. Air conducts heat about 15,000 times more slowly than a dense metal like steel.
15,000 times.
Right, so by packing a thick layer of cheap, localized rice husks around the outside of her combustion chamber, Maya is essentially wrapping the fire in a thick blanket of trapped air. The thermal energy hits that layer of air, gets trapped, and is forced violently back inward, compounding the heat inside the flame.
And because all of that compounded extreme heat is trapped inside that vertical heat riser, it creates a powerful physical phenomenon called the stack effect or draft.
Yes, thermodynamics dictates that hot air expands and becomes significantly less dense than cold air. Because it is less dense, it rapidly rises.
Basic physics.
Exactly. As this superheated 1,000-degree air violently shoots up the insulated vertical chimney, it creates a low-pressure zone, basically a vacuum, at the bottom of the stove right at the burn tunnel.
And nature abhors a vacuum. What does that low-pressure zone do?
It aggressively pulls. It sucks fresh, cold, oxygen-rich air in through the feed tube right underneath the burning sticks. This creates a high-velocity, self-sustaining feedback loop.
Oh, wow.
The hotter the vertical riser gets, the stronger the draft becomes. The stronger the draft, the more fresh oxygen is blasted into the primary combustion zone. The more oxygen, the hotter the fire gets.
It creates a miniature jet engine. And that high-velocity airflow, violently sucking air in and blasting fire up, creates this intense, low-frequency roaring sound, which is exactly why it earned the name rocket stove.
When you look at the humanitarian impact of Maya implementing this specific elegant engineering design, the numbers are just staggering. Because the combustion is nearly complete, and because the heat transfer is directed straight up to the cooking pot rather than blowing around in the wind, these rocket stoves reduce fuel consumption by 50 to 90% compared to an open three-stone fire.
Wait, 50 to 90% reduction in fuel?
Yes.
If we tie that back to your reality as a listener, think about what that means for a family in the Rohingya camps. They no longer need to spend 6 hours a day trekking into the hills, risking violence or injury, to forage for massive logs. They don't need axes. They don't need saws. Maya's curriculum explicitly notes that a rocket stove runs incredibly efficiently on twigs, pine cones, dried stalks, and fallen branches. It runs on the detritus that you can gather by hand in a few minutes.
And fundamentally, most importantly, the air inside their shelter is suddenly clear. The lethal, unburned particulate matter is gone, consumed as fuel. The engineering directly, measurably saves lives.
So Maya has the thermodynamic blueprint. She knows exactly how the air and the fire need to move. But now she hits a massive physical roadblock. What material does she actually use to build the core of this stove? I mean, if I am building a chamber that deliberately traps heat to push temperatures over 1,000 degrees Celsius, I can't exactly go to the local scrapyard and use standard sheet metal or an old oil drum.
No, you absolutely cannot. Standard thin steel or iron will undergo rapid oxidation at those temperatures. In the highly corrosive, superheated environment of contained wood fire, standard metals will warp, flake apart, rust through, or straight up melt into slag in a matter of weeks.
Just completely melt down.
Yes. Even highly specialized, expensive industrial alloys degrade over time in those conditions. Maya needs a material that is born from extreme heat.
Which means she needs to look backward. She needs humanity's oldest, most resilient technology.
She needs clay.
We are transitioning from the physics of flowing gases to the ancient science of dirt. But the CM Tech curriculum is incredibly strict on this point. Clay is not just mud. If you go into your backyard after a rainstorm and scoop up wet dirt, you don't necessarily have clay. What is it, really, on a chemical level?
Calling clay mud is a profound disservice to its geological and chemical complexity. Clay is a highly specific mineral classification. It is composed primarily of hydrous aluminum phyllosilicate minerals.
Okay, let's translate that for the listener. Phyllosilicate, what does that actually look like?
Phyllo comes from the Greek word for leaf. Think of baklava or phyllo dough, layers upon layers of incredibly thin sheets.
Oh, like the pastry.
Right. On an atomic level, clay is made of aluminum, silicon, and oxygen ions bonded together into perfectly flat, microscopic, plate-like structures.
And when you say microscopic, you really mean it. The module defines clay strictly by particle size. A particle of clay is smaller than 2 micrometers, that is 0.00002 millimeters. It is completely invisible to the naked eye.
And that unimaginably tiny size is the secret to everything clay does. Because the particles are so infinitesimally small, and because they're shaped like flat plates rather than round spheres, clay has an absolutely massive surface area relative to its actual volume.
Why does surface area matter so much for Maya?
Because of how it interacts with water. When you add water to clay, The water molecules are drawn to the immense surface area of these microscopic plates. The water forms an incredibly thin, lubricating film between the layers.
Okay.
The plates stick together due to chemical attraction, but that water layer allows them to easily slide past one another without separating.
It's like taking a brand new deck of playing cards and getting them soaking wet. If you press them together, they stick into a solid block, but you can effortlessly fan them out or slide them into a new shape.
That is a perfect visualization. That ability to slide and hold a new shape is called plasticity. It is what allows Maya, or a potter, to take a lump of clay and mold it, stretch it, or spin it on a wheel into a complex cylinder for her heat riser.
And then it dries, right?
Right. When the water eventually evaporates and dries out, those flat plates settle down against each other and form rigid hydrogen bonds, holding the shape perfectly.
It's fascinating how ubiquitous this material is. I love the anecdote in the sources about the origin of the word pothole. It ties right into how ancient and accessible clay is.
Yes. Historically, high-quality veins of clay were highly prized. Before paved roads, when a potter found a good vein of plastic clay running across a dirt path or a trade route, they would literally just dig it right out of the ground to make their pots, leaving a massive hole in the road.
That is so literal.
Thanks to the term pothole. It is a technology that is literally right under our feet.
But Maya quickly learns that not all potholes are created equal. The sources lay out a very strict clay hierarchy. This hierarchy is dictated by two things: the size of the microscopic particles and the temperature the clay can withstand before melting. This dictates exactly what Maya can use.
Let's run through what Maya is evaluating. At the absolute base of the hierarchy, we have earthenware.
This is the most common stuff, right?
Yes, earthenware is the oldest and most abundant form of clay. It has relatively coarse particles closer to that 2-micrometer limit, and it usually contains a lot of mineral impurities, primarily iron oxide.
The iron.
That iron is what gives earthenware its classic red terracotta color.
Think of standard red bricks or those classic orange flower pots you buy at the gardening center.
Exactly. Because of the impurities and coarser particles, earthenware matures at a relatively low firing temperature, usually between 600 and 1100 degrees Celsius. However, even after it is fired, because the particles are larger, it remains somewhat porous. Water will slowly seep through an unglazed earthenware pot.
Which is fine for a flower pot, but maybe not great if Maya wants to build something structural. So she looks at the next level up. Stoneware.
Stoneware is a significant step up. The particles are finer, and it contains far fewer iron impurities, so it usually fires to a gray or buff color. It requires a much higher firing temperature, typically between 1200 and 1300 degrees Celsius.
And at that temperature, the chemistry changes, right?
Dramatically. At 1300 degrees, the stoneware becomes incredibly dense, highly durable, and completely non-porous. It becomes literally stone-like. This is what your heavy, high-quality dinner plates, durable coffee mugs, and heavy-duty cookware are made from.
And if Maya wants the absolute peak of refinement, she looks at porcelain, also known as kaolin.
Porcelain is the diva of the clay world.
The diva.
It is made from extremely fine, incredibly pure silicate particles. It has almost zero impurities, firing to a brilliant, stark white. It requires the highest temperatures for domestic ceramics, between 1260 and 1400 degrees Celsius. When fired, it becomes completely non-porous, and if a potter throws it thinly enough, it is actually translucent. You can hold a porcelain teacup to the light and see the shadow of your fingers through the wall.
That's beautiful, but Maya isn't making teacups. She's making the core on a 1,000-degree rocket stove. Earthenware might slowly degrade, and porcelain is too delicate to cast thick walls, so she lands on the industrial workhorse: fire clay.
Fire clay is exactly what Maya needs for a combustion chamber. It is a highly pure clay, specifically very high in alumina content. Alumina is incredibly refractory, meaning it resists heat.
Okay.
Fire clay can withstand extreme thermal shock and temperatures well over 1600 degrees Celsius without melting or warping. It is the ultimate thermal armor used to line industrial furnaces and kilns.
But here is the crux of Maya's problem, and a major focal point for the incarcerated learners physically building these stoves in the CM Tech module. Transforming that soft, wet plastic fire clay into impenetrable thermal armor requires a terrifying journey through fire. You don't just set the clay out in the sun, you have to subject it to a series of violent, irreversible chemical transformations.
And that journey is fraught with physical danger.
Let's talk up a safety protocol. Maya is prepping her wet fire clay to mold the heat riser. What is the absolute biggest safety hazard she or an adult learner in the CM Tech workshop needs to mitigate before that clay ever gets close to a fire?
The single greatest danger is trapped air. If Maya does not properly prepare her clay using a process called wedging,
Ujing.
which is essentially a highly aggressive, systematic form of kneading the clay to align the particles and push out bubbles. If she doesn't do that, she might leave a tiny, invisible pocket of air trapped inside the thick wall of her ceramic cylinder.
It seems so innocuous, a tiny air bubble. Why is that lethal?
Because of the physics of thermal expansion. When Maya places that dried piece of clay into a kiln or a fire, the ambient heat transfers into that air pocket. As gas heats up, it expands rapidly and violently.
And the clay around it is simultaneously getting harder, right?
Exactly. The surrounding clay has lost its water, lost its plasticity, and is becoming rigid. The expanding superheated air inside the wall has absolutely nowhere to go.
Oh no.
The internal pressure builds exponentially until the rigid clay wall catastrophically fails. The piece doesn't just crack, it detonates.
It explodes.
It becomes a literal clay bomb, violently exploding and sending sharp, jagged ceramic shrapnel flying in every direction inside the kiln or the fire. In a group learning environment, or if someone is standing over the stoves, it can cause severe injury or blindness.
Okay, so Maya wedges the clay meticulously. She gets every microscopic bubble out. She builds the cylinder, lets it dry, and begins the firing process. Walk us through the gauntlet of temperatures. What is happening to the clay chemistry as the heat rises?
It happens in very distinct, non-negotiable stages. First, as the fire reaches 100 degrees Celsius, the physical ambient water trapped between the microscopic plates boils and evaporates. Maya has to raise the temperature incredibly slowly here, or the sudden creation of steam will crack the piece from the inside.
Once it's bone dry, we push hotter, between 200 and 400 degrees Celsius.
At this stage, any organic impurities trapped on the clay, bits of roots, leaves, or carbon, combust and burn out, leaving the clay pure.
And then we hit the point of no return, 450 to 600 degrees Celsius.
This is where mud ceases to be mud. At this temperature, the actual crystal structure of the phyllosilicates permanently reorganizes. The chemical water, the hydroxide ions that were physically bonded into the mineral structure itself, are violently driven off.
Wow.
Once this happens, the material is fundamentally changed. Even if you took that fired piece and soaked it in a bucket of water for 100 years, it would never dissolve back into plastic moldable clay. It is ceramic.
And tucked inside that critical range is a deeply perilous, fascinating moment for the material. Exactly 573 degrees Celsius. The curriculum calls it the quartz inversion.
This is a phenomenal piece of material science. Clay naturally contains varying amounts of silica or quartz crystals. At exactly 573 degrees Celsius, those quartz crystals absorb enough thermal energy to suddenly shift their atomic structure. They transition from what is called an alpha quartz state to a beta quartz state.
And what does that mean in physical reality?
It means the atomic bonds change angles, and the crystal physically increases in volume by about 1 to 2%. The quartz literally instantly swells.
It's like the material takes a sudden, violent breath.
That is exactly what happens. And if Maya's kiln is heating up too fast, or conversely, if it is cooling down too fast as it passes back through 573 degrees and the quartz shrinks again, that sudden volume change will rip the ceramic piece apart. It will shatter. She has to baby the fire through that specific temperature.
But if her piece survives the quartz inversion, she pushes into the extreme final heat, sintering and vitrification.
Sintering occurs between 800 and 1,000 degrees. The individual microscopic particles of clay start to physically fuse together at their sharp edges, creating a solid, continuous matrix. Finally, between the 1,000 and 1,400 degrees, depending on the specific clay body, you achieve vitrification.
Vitrification comes from the Latin word for glass, right?
Yes. At this extreme temperature, the silica content in the clay actually begins to melt into a liquid glass-like phase. This molten glass flows into the microscopic pores and voids between the fused clay particles.
That's incredible.
When the piece eventually cools, that glass hardens, locking everything together into a rock-hard, permanent, completely watertight ceramic. Maya has successfully created her thermal armor.
It is an incredible triumph of applied science. We have spent time marveling at the beauty of this chemical process and the incredible utility of clay and fired bricks, but we cannot responsibly explore this topic without looking at how these materials are actually manufactured today in many parts of the world.
Right, the real-world supply chain.
Maya is working in South Asia, and if she needs to source fired bricks for the outer housing of her stoves, she has to confront the supply chain. We have to talk about the human cost.
It is a dark, necessary pivot. The reality of modern brickmaking in South Asia is a stark, horrifying contrast to the elegance of the material science we just discussed.
The sources provided for this module include deeply researched reports from the International Justice Mission, or IJM. They investigated the brick kiln industry in India, and it is devastating to read. We're not talking about automated factories, we are talking about blood bricks.
The sheer scale of the industry is almost unfathomable. The IGM reports that India alone has over 100,000 operating brick kilns, and those kilns employ roughly 23 million workers.
23 million people.
Yes. And the conditions detailed by the investigators are nothing short of modern-day slavery, driven by predatory debt bondage. Entire families are tricked into taking small loans and then forced to work in the kilns to pay them off. A debt that manipulative owners ensure is never actually cleared.
The physical realities of that bondage are laid out in the module. The living conditions, the reports state that entire families are forced to live on site in cramped 7.6 square meter spaces.
It's awful.
If you're trying to visualize that, 7.6 square meters is roughly the size of a small walk-in closet or a solitary confinement cell. And nearly 88% of these kilns only provide access to untreated, heavily polluted groundwater. 75% of the toilet facilities don't even have running water.
But the most heart-wrenching aspect of the IGM report, the part that truly grounds the urgency of this module, focuses on the children. The investigators found that between 65 and 80% of children under the age of 14 who live at these kilns are forced to work 9 or more hours every single day.
They're working shifts that start at 4 a.m. and run straight through the blistering heat until 11:00 a.m. in environments completely saturated with silica dust and toxic chemical pollutants from the burning coal.
The physical toll on a child's developing body is catastrophic, carrying stacks of heady, wet mud bricks on their heads, breathing in the ash. They suffer from severe respiratory illnesses, stunted growth, and chronic pain. The report quotes a child who couldn't remember a single day of ever playing. Their bodies simply hurt too much to move after their shift.
That's just so heavy.
They are completely cut off from the education system, locked into a generational cycle of brutal manual labor. So if we connect this to the bigger picture, we have to ask how engineering can liberate these people.
It is overwhelming. And for Maya and the learners at CM Tech, it poses a profound ethical crisis. If you are an engineer tasked with building infrastructure, how do you do it without participating in that system of slavery?
Right.
And the module's answer is brilliant. It doesn't just present this horror as a tragedy to be pitied, it uses it as a catalyst for rigorous design thinking. How can an understanding of thermodynamics and geometry systematically disrupt an industry built on human suffering?
That is the power of engineering as liberation. Maya realizes she can't instantly change the economic laws of debt bondage, but she can change the brick. She can design smarter. Let's look at the standard brick. It is a solid block of fired clay. It is incredibly heavy. It requires an immense amount of manual labor to dig the solid mud, mold it, carry it while wet, and load it into a kiln.
Right.
But Maya asks a subversive question. What if the brick didn't need to be solid?
Right. We talked earlier about how air is a phenomenal insulator. So Maya looks at incorporating porosity into her bricks. How does she achieve that using the local materials in the camp?
She goes back to the agricultural waste. Maya takes organic material like sawdust or the rice husks we used for the stove insulation and mixes it directly into the wet clay before molding the brick.
So she has a brick that is essentially half mud, half rice husks. What happens when she fires it?
The extreme heat of the kiln bakes the clay rigid, but it simultaneously incinerates the organic matter. The rice husks completely burn away into ash and gas, leaving behind millions of tiny, interconnected voids, microscopic pockets of trapped air inside the solid structure of the brick.
She creates a rigid sponge.
Exactly. This gives the brick a controlled porosity of 20 to 30%.
And the immediate physical result is that the brick is instantly 20 to 30% lighter.
Lighter bricks drastically reduce the physical burden on the workers. A child or a worker is suddenly carrying significantly less weight per load. But structurally, it is also a vastly superior product for the stoves.
How so?
Because the brick is riddled with air pockets, it conducts heat thousands of times more slowly than a solid brick. It becomes a highly insulative building material. Maya has used chemistry to reduce the raw material needed, reduce the labor required to carry it, and improve the thermal performance.
It's the definition of working smarter, not harder. But Maya doesn't stop at the chemistry of the brick. She looks at the geometry of what she is building. The module challenges the learners to analyze the shape of the rocket stove. Why are Maya's heat risers perfectly cylindrical instead of just a square chimney built out of flat bricks?
It comes down to structural analysis and the distribution of external forces. A flat, rectangular wall is inherently weak against perpendicular force. If pressure pushes against the middle of a flat wall, all the stress concentrates at that single point, causing it to bend inward and eventually crack.
But a curved wall changes the math entirely. If you think about the pressure hull of a deep-sea submarine, it's not a rectangular box, it's a perfect cylinder.
That is the perfect visualization. A curved wall, like a cylinder or an arch, is inherently strong because it takes any localized force applied to it and continuously distributes that stress outward along the entire curve of the surface.
Because of that inherent geometric strength, Maya realizes she can build her cylindrical walls much, much thinner than if she were building a flat, square wall and still achieve the exact same or better structural integrity.
And thinner walls mean using drastically fewer bricks. Less material needed overall means less demand on the kilns, which means less brutal manual labor required to dig and fire the clay. By applying the simple physics of arches and cylinders, Maya systematically reduces the raw demand that fuels the blood brick industry.
Okay, so Maya has optimized the shape of the brick and the shape of the wall to reduce the reliance on fired clay. But she is still relying on firing clay at massive temperatures, which requires fuel and kilns. Is there a way to build durable structural housing for these stoves without firing materials at all? Can she use a chemical binder instead of a thermal one?
Oh, this is where it gets really fun.
This exact question leads us to one of the most incredible historical detective stories in the curriculum. We are talking about Roman concrete.
This is a phenomenal pivot from thermal engineering to chemical engineering. For decades, modern materials scientists have been deeply humbled and baffled by ancient Roman structures.
It is the ultimate engineering mystery. You look at a structure like the Pantheon in Rome. Its massive, unreinforced concrete dome spans over 140 feet. It was completed around 128 CE, nearly 2,000 years ago, and it is still standing, perfectly intact, surviving millennia of earthquakes and weather.
Meanwhile, modern engineers built a steel-reinforced concrete bridge in the 1970s, and 50 years later, it is cracking, spalling, and requires millions of dollars in emergency repairs. The disparity is embarrassing. What did the Romans know about chemical binders that we somehow forgot?
For the longest time, modern scientists thought the Romans were just kind of lazy builders.
It is true. When scientists put samples of ancient Roman concrete under the microscope, they kept noticing these small, bright, white chunks scattered throughout the material. These chunks are called lime clasts. For decades, the scientific consensus just dismissed these clasts as evidence of sloppy mixing. They assumed the ancient laborers just didn't sift their materials well enough, leaving lumps of unmixed lime in the mortar.
Imagine looking at the Pantheon, a 2,000-year-old architectural miracle that defies modern replication, and concluding, yeah, the guys mixing the cement were just really sloppy.
It is incredible hubris. But that all changed in 2023. A brilliant team of researchers led by MIT professor Edmure Masick finally cracked the code.
Yes.
Masick's team proved that those white lime clasts were not a mistake. They were entirely intentional, highly engineered, and they were the absolute secret to the concrete's 2 millennia survival rate. They discovered the Romans used a technique called hot mixing.
Okay, let's unpack hot mixing for the listener who hasn't spent time on a masonry crew. Normally, if you are making traditional mortar from scratch, you start with quicklime, which is calcium oxide. You have to slake it first. What does slaking actually mean?
Quicklime is essentially limestone that has been baked in a kiln to drive out all the carbon dioxide. It is incredibly unstable and violently reactive. If you touch dry quicklime with sweaty hands, it will react with the moisture and literally cause chemical burns.
Oh, wow.
Slaking is the process of soaking that dangerous dry quicklime in a large vat of water. It boils, hisses, releases mass amounts of heat, and eventually settles down into a safe, wet, stable paste called calcium hydroxide, or slaked lime. You take that safe paste and mix it with your sand and aggregate to make mortar.
So you tame the chemical before you use it?
Exactly, you tame it.
Ah.
But Masick's team discovered that the Romans didn't tame it. They skipped the slaking process entirely. The Romans took the dry, violently reactive quicklime and mixed it directly with dry volcanic ash. Then they added water to the entire dry mix.
Which triggers an immediate, aggressive chemical reaction.
A violent exothermic reaction. The heat generated within the mixing trough was intense, and that extreme, localized heat physically altered the chemistry of the mix. It prevented the quicklime from fully dissolving evenly, purposefully creating those brittle, nanoparticulate lime clasts scattered throughout the concrete.
So the Romans purposely left highly reactive, brittle chunks of lime inside their walls. Why does having brittle chunks in your concrete make it last 2,000 years?
Because it creates an autonomous self-healing mechanism. Concrete, no matter how well you pour it, will inevitably develop microcracks over time due to the ground settling, thermal expansion, or seismic activity. When a microcrack forms in Roman concrete, it naturally propagates through the path of least resistance. And the weakest points in the matrix are those brittle line clasts. The crack physically breaks the line clast open.
Okay, so you have a crack with exposed quicklime inside it.
Then it rains. Rainwater seeps into the crack. As soon as the water hits that exposed, highly reactive lime clast, it dissolves the calcium, instantly creating a highly concentrated calcium-saturated solution within the crack.
And here is the magic trick.
As that calcium-rich solution reacts with the surrounding pozzolanic volcanic ash, pozzolanic meaning it reacts with calcium hydroxide to form cementitious compounds, or even just reacts with the carbon dioxide in the air, it recrystallizes as solid calcium carbonate.
It literally grows new stone inside the crack.
It precipitates new mineral deposits, perfectly sealing the crack shut before the fissure can ever spread deep enough to threaten the structural integrity.
It's like baking a cake that has the ability to fix its own cracks. The moment the cake cracks, the repair kit ruptures, bleeds calcium, and knits the cake back together. And the MIT team proved this in a lab in 2023. They made modern concrete using the Roman hot mixing method, deliberately cracked the blocks, ran water through them, and within 2 weeks, the cracks had completely sealed themselves. The water stopped flowing.
And if we tie this incredible discovery back to Maya Torres and her mission in the Rohingya refugee camps, the implications are immense. Maya realizes she doesn't need a multi-million-dollar industrial chemical plant to make self-healing concrete.
Right?
The high temperatures generated by the rocket stove she just built can be used to calcine local limestone into quicklime. She can take that quicklime, mix it with the ash left over from burning the rice husks, because rice husk ash is highly pozzolanic, just like the Roman volcanic ash, and she can create a localized, sustainable, self-healing building material entirely out of agricultural waste and local rocks.
It is a stunning full-circle moment for her design. But the CM Tech module doesn't let the learners stop at ancient Rome. The innovation in concrete is pushing forward rapidly today. Our sources highlight a brand new, modern marvel called Dare2C.
Yes, Dare2C. It is an acronym that stands for Durable Aluminium Reinforced Environmentally Friendly Concrete Construction. It is a massive research project out of SINTEF, an independent research organization in Norway, led by Chief Scientist Harold Justice. And Dare2C specifically targets the massive looming climate disaster of modern Portland cement.
Let's talk about that climate footprint because it is staggering. The sources note that standard cement production is responsible for between 5 to 8% of all global anthropogenic CO2 emissions, just making the powder.
It is a massive polluter. To make Portland cement, you have to heat limestone and clay in massive rotary kilns to 3,450 degrees Celsius. Not only does burning the fuel to reach that temperature release carbon, but the chemical decomposition of the limestone itself off-gasses huge amounts of CO2.
So how does the Dare2C project fix this?
Dare2C mitigates the emissions by aggressively cutting the amount of Portland cement needed. They replace up to 50% of the traditional cement with something called calcined marl, or calcined clay.
Define calcined for the listener. We use that word with limestone, but what does it mean for clay?
Calcining simply means thermally treating a material to bring about a chemical or physical change without actually melting it. In this case, they heat the raw marl clay to about 700 or 800 degrees. Just like we discussed with the quartz inversion and driving off the chemical water, this heat physically changes the crystal structure of the clay, making it highly reactive. It makes it pozzolanic, so it will react with the remaining cement to form a strong binder.
Replacing 50% of the cement is a huge carbon win. But the module notes that the real revolutionary breakthrough of Dare2C isn't just the clay, it is the reinforcement inside the concrete.
Exactly. Concrete has incredible compressive strength, you can park a tank on it, but it has terrible tensile strength. If you bend it, it snaps. That is why we reinforce it with heavy grids of steel rebar. But steel has a fatal flaw. It rusts.
And when steel rusts inside concrete, it expands, causing the concrete to spall and explode outward. To stop the steel from rusting, builders have to bury it deep. They use a thick layer of concrete, usually 50 to 70 millimeters thick, just as a protective cover to keep water and oxygen away from the steel.
Which means we are pouring millions of tons of excess concrete globally just to act as a weather shield for the steel. The logical solution would be to use aluminum rebar instead. Aluminum is significantly lighter, and it develops a natural oxide layer that protects it from rusting in the same destructive way steel does.
So why aren't our bridges filled with aluminum rebar?
Because of a very explosive chemical problem. Traditional Portland cement creates a highly alkaline environment as it cures. It produces a massive amount of calcium hydroxide. If you embed an aluminum bar in that highly alkaline wet cement paste, a violent chemical reaction occurs. The alkaline environment actively attacks the aluminum, stripping away its protective oxide layer and generating hydrogen gas.
And gas inside wet concrete is a disaster.
Complete disaster.
Uh,
The concrete vigorously bubbles and foams around the aluminum bar, creating massive sponge-like cavities. When the concrete finally hardens, the structural bond between the metal and the concrete is completely destroyed. The rebar just slides right out.
So how does Harold Justness and the Dare to See team solve the bubbling aluminum problem?
The secret is returning to that 50% replacement with the calcined marl. The calcined marl acts as a chemical sponge. It is incredibly hungry for calcium hydroxide. As the remaining Portland cement hydrates and starts producing that dangerous alkaline hydroxide, the calcined marl rapidly consumes it, binding it up into solid cementitious compounds.
Wait, it eats the alkaline poison before it can attack the metal.
Precisely. By aggressively consuming that hydroxide, the marl keeps the overall alkalinity of the concrete low enough that the aluminum's protective oxide layer remains perfectly intact.
The proof of concept documented in the source material is amazing to visualize. They literally poured 2 clear cups of wet concrete, 1 standard Portland mix, 1 Dare to See mix, and stuck a raw aluminum plate into each. The standard concrete instantly started bubbling like a witch's cauldron, leaving massive structural gas voids pressed right against the metal. But the Dare to See mix, it was completely inert. Smooth as glass, the aluminum was perfectly protected.
This changes the entire paradigm of construction. Because the aluminum is chemically protected by the marl and naturally resists corrosion, you no longer need that massive 50 to 70 millimeter protective concrete cover. You can reduce the outer cover to just 20 millimeters.
Less cover means you use drastically less concrete per column, per floor, per bridge. You've already cut the carbon-heavy cement content by 50% using the calcined clay, and now you are pouring significantly less concrete overall and reinforcing it with a much lighter metal. The compounding carbon savings and weight savings is a massive leap forward for global sustainable building.
And, incredibly, the Dare to See chemistry offers one more massive benefit for coastal regions. Because they aren't worried about chloride-induced rusting of steel rebar, the Dare to See concept actually allows builders to use raw seawater as the mixing water, rather than relying on precious purified fresh water.
Wow.
This is a holy grail for construction in water-scarce regions or island nations.
Okay, we're seeing how deeply understanding the fundamental chemistry of materials, from ancient Roman hot mixing to modern calcined clay sponges, unlocks these incredible world-altering capabilities. But I want to bring this entirely back down to earth, back to the incarcerated learners at CM Tech and back to Maya in the refugee camp.
Yes, the practical application.
We have spent the last hour talking about how amazing ceramics, bricks, and calcined clays are. But all of these materials share one massive bottleneck. They require serious, extreme heat. Earthenware needs 1,000 degrees, porcelain needs 1,300 degrees, calcine and clay needs 800 degrees. If you are Maya in a remote camp, or if you are an adult learner taking this module inside a correctional facility, how do you actually achieve that high-tech, high-temperature firing capability without building a massive, expensive, energy-hogging industrial brick kiln?
This question brings us to some cutting-edge, almost unbelievable research published in 2025 in the journal Applied Sciences by researcher Bruno Gaffay. We're looking at the revolution of the microwave kiln.
I read this section 3 times. Are we talking about using a literal standard kitchen microwave to fire ceramics?
We are. Gaffay's study rigorously demonstrated that with the proper internal insulation, a heavily modified standard domestic microwave oven, the exact same appliance you use to reheat pizza, can be used to fire ceramics to temperatures exceeding 1,280 degrees Celsius.
12,280 degrees. Inside a kitchen appliance, how long does it take to reach that temperature?
This is where it completely disrupts the industry. It achieves that 12,280 degrees in just one single hour.
Wait, 1 hour?
To put that in perspective for the listener, a conventional electric ceramic kiln, which requires heavy 220-volt wiring and massive heating coils, takes between 8 to 10 hours to slowly ramp up to that temperature and then another 12 hours to cool down. The microwave kiln technology reduces the total energy consumption by over 97% per volume compared to small conventional kilns. It is blisteringly fast and hyper-efficient.
Okay, wait. I am going to push back here on the physics. You are putting raw, dried clay into a microwave to get it to 1200 degrees. But microwaves work by emitting electromagnetic radiation that specifically excites and vibrates water molecules, right? The friction of the vibrating water is what heats my coffee. But as we discussed during the firing gauntlet, once the clay passes 100 degrees Celsius, it is bone dry. There is no water left. So the microwave should just pass right through the dry ceramic without transferring any heat at all.
You have hit on the exact physical hurdle of the technology. You are entirely correct. Cold, dry ceramics are essentially transparent to microwave radiation. In physics terms, they have a very low dielectric loss factor. They do not absorb the energy. To solve this, you need a hybrid heating approach. You need a middleman.
A
You
middle.
need a material that sits inside the microwave next to the clay, catches the microwaves, and converts them into radiant heat to jumpstart the process until the ceramic gets hot enough to start absorbing the microwaves itself.
And what is that middleman called?
It is called a susceptor.
And what is a susceptor made of? Because I was taught very strictly as a child never, ever to put metal in a microwave unless I wanted to burn the house down.
In high-end industrial applications, susceptors are usually made of highly specialized, expensive materials like pure silicon carbide rods. But Goffey's research, which aligns perfectly with CMTech's ethos of accessible engineering, focused on creating homemade DIY susceptors using incredibly cheap, accessible mineral powders. And the magic recipe he developed is a precise mixture of silicon carbide powder and submicroscopic magnetite powder.
Magnetite, that is an iron oxide. That is literally a highly magnetic iron ore. So you are putting metal in the microwave.
We are, but the form factor is crucial. It is in a very specific submicroscopic powder form mixed into a matrix. If you put a solid fork in a microwave, the shape causes electrical arcing. But the powdered magnetite has exceptional microwave absorption properties without arcing. It acts as the thermal catalyst. When you turn the microwave on, the magnetite instantly absorbs the electromagnetic radiation and heats up violently. In fact, if you microwave pure magnetite powder by itself, it gets so hot, so fast, that it will literally explode, forcibly emitting oxygen gas and transforming into red hematite.
Whoa. So if it wants to explode, how does Goffey stop his DIY susceptors from detonating inside the microwave?
You tame it by mixing it. You blend the magnetite with the silicon carbide powder and add a little bit of silica or alumina sand to act as a structural skeleton. You press this mix into small pucks or crucibles. The heat generated by the magnetite jumpstarts a remarkable, complex chemical reaction within the susceptor itself.
Walk us through that chemistry. What happens inside the puck?
As the magnetite rapidly pushes the temperature past 850 to 950 degrees, it begins to chemically react with the silicon carbide. The silicon carbide breaks down and decomposes. It combines with the iron from the magnetite to form an entirely new iron silicide mineral called ferrosilicon, specifically a rare mineral structure called gupiate. And as a byproduct of this transformation, the susceptor begins actively releasing carbon monoxide gas.
Okay, let's freeze frame and visualize this. You have a domestic microwave running. Inside is a heavily insulated box. Inside that box are these homemade pucks of mineral powder surrounding a clay pot. The magnetite catches the microwaves, gets incredibly hot, forces the silicon carbide to break down into gupiate, and pumps out carbon monoxide gas. And this intense chemical ballet happens in a matter of minutes.
Minutes. The extreme rapid heat radiating from these susceptor pucks completely bathes the raw ceramic piece in thermal energy. And here's the beautiful part of the hybrid heating. Once the ceramic piece absorbs enough of that radiant heat to reach around 400 to 600 degrees Celsius, its own dielectric properties fundamentally change.
Oh, so it stops being transparent to the microwaves.
Exactly. The hot clay begins to absorb the microwaves directly. So now the ceramic is being heated from the inside out by the microwaves, while simultaneously being heated from the outside in by the glowing susceptors. This hybrid dual heating ensures the piece fires evenly and incredibly rapidly, avoiding the catastrophic thermal shock that would normally shatter it.
And the sources detail that the carbon monoxide gas being pumped out by the susceptors isn't just an interesting byproduct. It serves a highly prized, crucial function for the ceramist.
This raises an important point about the intersection of artistry and chemistry. In traditional high-end ceramics, artists often desire what is called a reducing atmosphere inside their kiln.
What does reducing mean in this context?
It means an environment that is starved of oxygen. A reducing atmosphere chemically alters the glazes painted on the pottery. Because the fire is starved of oxygen, it aggressively pulls oxygen atoms out of the metal oxides in the glaze. This chemical reduction creates incredibly beautiful, highly specific colors, like vibrant copper reds or deep celadon greens, that are chemically impossible to achieve in a normal, oxygen-rich environment.
And normally, if I am a potter, I can only get a reducing atmosphere if I own a massive, expensive gas kiln. I have to manually choke off the air dampers so the gas fire starves and produces soot and carbon monoxide. I can't do it in this standard electric plug-in kiln because the metal electric heating coils need an oxidizing environment. Otherwise, they instantly degrade and snap.
Exactly. But the microwave kiln completely upends that limitation because the microwave is using electromagnetic waves rather than exposed metal coils, and because those magnetite-rich susceptors are naturally generating liters of carbon monoxide gas as they heat up, the enclosed crucible naturally creates a strongly reducing atmosphere.
So a student can achieve high-end atmospheric gas kiln glaze effects using electricity in a fraction of the time, using homemade susceptors that cost literal pennies to make.
It is the ultimate democratization of high-end manufacturing. An adult learner in a correctional facility or an artisan in a developing nation or Maya in her refugee camp can literally build a 1200-degree reducing kiln out of a broken kitchen appliance, some abrasive polishing powder, and iron dust. It completely removes the financial and spatial barriers to entry for producing advanced ceramics.
So we have covered an immense amount of ground today. We've gone from thermodynamics to brick kilns to microwaves. And I want to ask the ultimate so what question for you, the listener, sitting in your car or your kitchen right now. Why should you care so deeply about making it easier and cheaper to produce ceramics? Because it connects directly to one of the most insidious, terrifying health crises of our modern era, microplastics.
The pervasive contamination of microplastics is a global ecological and biological emergency. In recent years, peer-reviewed studies have consistently found microplastics deep inside human blood, in breast milk, embedded in deep lung tissue, and recently they have documented microplastics crossing the blood-brain barrier and accumulating in human brain tissue.
We are literally marinating our cellular structure in plastic, and a massive vector for this contamination is how we store and heat our food. When you heat food in plastic Tupperware, or even just store highly acidic foods like tomato sauce in plastic containers, the heat and acid break down the polymer chains. They leach endocrine-disrupting chemicals like BPA and thousands of microplastic particles directly into the food you are about to eat.
Which is exactly why a widespread, accessible return to ceramics is so vital for public health. Think about the properties of the vitrified stoneware we discussed earlier. High-fired ceramics are chemically inert. They're essentially glass. They do not leach chemicals. They do not shed microplastics into your food. They can withstand any oven or cooking temperature safely. And at the end of their life cycle, whether they break tomorrow or in 1,000 years, they are totally biodegradable. They just return to the earth as crushed rock exactly as they started. The ancient solution, clay fired in extreme heat, is the exact perfect answer to our modern high-tech toxic plastic crisis. But until this recent research, making high-fired ceramics was incredibly energy-intensive, slow, and expensive. The microwave kiln technology we just explored makes it fast, cheap, and highly energy efficient. It makes a return to ceramic food storage scalable and accessible for everyone. It is the perfect synthesis of eras. We are using a modern technology, harnessing the electromagnetic spectrum, to hyper-accelerate humanity's oldest technology, clay, to solve a modern existential ecological disaster.
And that synthesis, that ability to connect the ancient with the cutting edge, is exactly what the incarcerated learners at Cadmore Polytechnic Institute are mastering in this module. Let's take a step back and really look at what they have accomplished by following Maya Torres' story. They aren't just taking a casual pottery class to pass the time, they are learning to map the fluid thermodynamics of combustion. They are dissecting the exact atomic phase changes of phyllosilicate minerals. They are engineering structural geometries to combat child slave labor in the international supply chain.
They are absorbing and applying MIT and Stanford-level engineering concepts, and they are doing it entirely through a lens of extreme empathy and humanitarian application. They're learning that this dense scientific knowledge isn't abstract or confined to a textbook. It is a tangible tool that can literally save 3.8 million lives from smoke inhalation or transform the carbon footprint of the global concrete industry.
It empowers them to look at the physical world around them and realize that it is malleable, it is not fixed, it can be challenged, and it can be redesigned.
Knowledge is most valuable when it is deeply understood and practically applied. And what the CM Tech module proves so beautifully is that sophisticated, world-changing engineering doesn't belong exclusively in an Ivy League laboratory. It belongs in the hands of anyone, anywhere, who is willing to understand the mechanics of fire and the chemistry of mud.
And that leads me to my final provocative thought for you, the listener. Think about the everyday, mundane objects that are surrounding you right now. A brick wall outside your window, a concrete sidewalk you walk on, the microwave sitting on your kitchen counter. We just spent an hour exploring how the Romans mastered self-healing concrete 2,000 years ago simply by changing the sequence of how they mixed it. We saw how mud and a modified kitchen microwave can create 1200-degree ceramic armor to fight microplastics. We saw how simply changing the shape of a burning chamber from a pyramid to a J-curve can save millions of lives.
The solutions to our greatest global problems are so often hiding in plain sight, waiting for us to combine ancient wisdom with a fresh perspective.
What other ancient, forgotten technologies are sitting right under our noses, just waiting for a modern tweak to completely change the world? Keep digging into the science of the everyday. Look closer at the fire and look much closer at the mud. The landscape might seem murky, but the answers are absolutely there if you know how to look. Thanks for taking the deep dive with us today. We'll catch you next time.